In this video, we will see how to write an assembly program for the IMAGine IP and export the program to be used in Vitas application projects. Before we can write assembly programs, we need to learn the instruction set of IMAGine and how to use the assembler. The assembler for IMAGine is provided as a Python module under the supplement directory. The Picasso assembler is used as a submodule in the IMAGine assembler. The assembler is implemented as a Python class. The programming interface has been exposed as some Python level, the module level functions. The instructions supported by the assembler are documented in the IMAGine ISA PDF under the doc directory. The document briefly discusses the internal architecture of IMAGine. The assembler supports two types of instructions: built-in IMAGine instructions and some macro instructions that implement some high-level functions using the built-in instructions. The assembler directive functions are needed to interact with the assembler. For example, setting up the assembler parameters, resetting the assembler internal state, exporting the assembled output in different formats, etc. Some example programs are included in the package in the EX directories. The EX1 example contains an IMAGine program to perform a basic matrix vector multiplication. Let's go to the work directory and walk through this example. The prog ex01 command copies the example program in the work directory so that we can edit and modify it without changing the original implementation. An assembly program for IMAGine is basically a Python script that uses the IMAGine assembler module to assemble the output program. At the beginning of the script, the assembler module needs to be imported. Because IMAGine deals with matrix and vectors, it supports and internally uses NumPy arrays. After importing the module, some parameters need to be set that corresponds to the target implementation of the IP. The load params directive loads the configuration for the 64 by 64 PE array implementation from the YAML file. If the implementation of the IP changes, this YAML file needs to be updated and the program needs to be reassembled for the target implementation. These are some names of the input-output files used in the body of the script. The data file can be assumed to be exported from PyTorch or TensorFlow after training a model. That is, the trained weights and biases are saved in the data file. The program header and cout files are the names of the files which will be generated by this Python script. At first, we read the data file, then extract the weights and biases. The data file also contains a test vector which is loaded in V. The main assembly program starts from here. These variables are declared to name the registers we will be using in the body of the assembly program. Similar to the CUDA-based GPU programming, before launching the compute kernel, we need to move data from the host CPU to the accelerator. These three macros are used to load the weight matrix, bias vector and the test vector into the PE registers. Note that the matrix and vectors are NumPy arrays. These macros internally converts the floating point numbers to their fixed point representation based on the assembler parameters, then changes their bit layout to match the columnar layout of the PU registers of IMAGine. These macros are data aware. This means that during assemble step, they will try to generate as less instruction as possible to write the matrix and vectors into the PU registers based on their values. For example, if you are loading a 64 by 64 matrix with all zeros, the load macro will simply clear the register. These directives are used to assemble and export the loader program as a C array. The reset directive is used to reset the internal state of the assembler because we will start writing the compute kernel in this same script. These instructions perform the operations of the linear layer of PyTorch. It multiplies the input vector stored in reg V by the weight matrix stored in reg A, then accumulates the products and then adds the bias vector stored in reg B. The VV serial enable instruction is needed to capture the output vector in the column shift register submodule. The sync instruction is needed to wait for the MV add instruction to finish before starting the parallel shift to push out the result vector to the output FIFO. This directive is used to export the compute kernel as a C array. The export header directive exports the header file for the program struct. Now let's assemble this program. The assembled outputs will be stored in the out directory. The assemble shell script shows how to assemble the program. The most important thing to notice is the Python path variable. This environment variable needs to be set to include the path of the assembler module. The assembler script failed because it could not find the assembler module. The output C programs containing the assemble program is generated. This header file contains the IMAGine program struct. The loader program does a whole bunch of writes to load the weights and biases. The compute kernel performs the GEMV operation on the program registers, then pushes the output vector to the output FIFO. This Python script extracts the test vectors from the data file and exports them as C arrays to run tests on the hardware. All these files can be generated running the assemble shell script. Now these source files can be imported into the Vitas project to execute the assemble program on IMAGine. Similarly, the other two examples can be assembled and run on the IMAGine IP. Note that these examples are assembled and combined with the driver sources and the main.c file under these example application projects. They can be included in a Vitas project and run on the hardware without going through this assembly process.